Hello, this is Math 2270 for summer of 2020, coming to you from the College of DuPage. And the title of this lecture is Introductory Matters, Definition. An equation containing the derivatives of one or more unknown functions, or dependent variables, with respect to one or more independent variables is said to be a differential equation, or DE. To talk about them, we classify them into types, order, and linearity. If a differential equation contains only ordinary derivatives of one or more unknown functions with respect to a single independent variable, be it x or t, it is said to be an ordinary differential equation, or ODE. An equation involving partial derivatives of one or more unknown functions of one or more independent variables is called a partial differential equation, or PDE. Many notations are used. We can use Leibniz notation, shown here. Sometimes we're using the prime notation. Now, Leibniz notation is really the best because it's very clear what you're taking the derivative with respect to, what is the independent variable, but sometimes that is considered understood from the context, and you need to think about that as you go forward. Sometimes in physical science and engineering, Newton's dot notation is used, so he would represent this differential equation as S double dot is equal to minus 32. Also, partial derivatives are often denoted by subscript notation, so this would be the second partial of u with respect to x is equal to the second partial of u with respect to t minus 2 times the first partial of u with respect to t. And sometimes we even will be using operator notation, where this will represent the nth derivative of with respect to an understood independent variable. The order of a differential equation is the order of the highest derivative in the equation. In symbols, we can represent an nth order differential equation in one or more independent variables by the form this equal to 0, where f is a real valued function and it's a function of the independent variable, be it t or x, the function itself, and the first n derivatives. We can also talk about whether they're linear or not. So an nth order ordinary differential equation is said to be linear if f, this one, is linear in those variables. This means that it's linear when it looks like this. Notice that the a's can be any function as long as they're only of one independent variable. And we can move the g of x to the other side, and that would be the same thing. Two very special cases that we will study is first order differential equations and second order differential equations. And so two characteristic properties to look for is the dependent variable y and all its derivatives are of first degree. That is, the power of each term involving y is 1, y and its derivatives. The coefficients depend at most on the independent variable x. A nonlinear ordinary differential equation is one that is not linear. Here are some examples. It is interesting, I think, that Newton's second law, F equals ma, can actually be described with a first order differential equation here, where we're saying it's the first time derivative, that acceleration is the first time derivative of velocity, or a second order differential equation where the acceleration is known to be the second time derivative of position. We have some other examples here. These are famous partial differential equations. This one is known as the heat equation. Also is used for diffusion epidemics and such. This one is called the wave equation, and that's used in quantum mechanics and other places. And so we have kind of a mix here. Let's test your understanding of these things. I want you to look at these examples, and with each one of them declare whether they are ODEs, PDEs, what is their order, Are they linear? Are they not linear? Or are they ambiguous. You cannot tell if they're linear or nonlinear. Let's see how you do. Let's see how you did. You see here you don't know what capital F is. It could be nonlinear or linear, and so you cannot answer that question. Which other ones are interesting? Number 6 is nonlinear because sine of y is sitting there. Here you see a fourth derivative. That's, I guess, interesting. And maybe that's enough. See you in section 6.1.